Good evening, class. We're going to pick back up with the final exam review. I believe we left off on number 10, which says to graph the function using the intercepts, multiplicity of roots, and end behavior. Again, we will not be doing any graphing on a multiple choice test, so I'm going to go ahead and skip that and go right to number 11, which deals with limits. All right, so 11 says find the limit if it exists, and 11a is the limit as x approaches 2 of 3x minus 7. All right, now remember with limits, the first thing you always want to try is direct substitution. So can I just go ahead and plug this 2 right in here? Yes, I can. If I do, 3 times 2 is 6, minus 7 is negative 1. So this limit is negative 1. Part B says the limit as x approaches negative 1 of 5x. So again, can I just direct substitute this right in? I sure can. And when I do, I get negative 5. All right, C. The limit as x approaches 2 of x plus 3 over x minus 2. All right, so when I try to plug this in, I get 5 over 0. All right, well, we can't have 0 in the denominator. All right, now when we get 0 over 0, which we'll get to in a minute, that's when we want to do our divide out technique. But when we get a number over 0, and it's an overall limit, not just a one-sided limit, we can always say that that limit does not exist. D, the limit as x approaches 2 of x squared minus 3x plus 2 all over x squared minus 4. So of course here we always want to try direct substitution. When we do that, we get 4 minus 6, which is negative 2, plus 2 is 0. On the bottom, 4 minus 4 is 0. So we get 0 over 0. All right, that's when we know we want to do the divide out technique. So I can factor the top to x minus 2 and x minus 1. And the bottom, x plus 2, x minus 2. Well, of course, my x minus 2's will cancel out. Now I do direct substitution again with what is left. So when I plug in a 2, I get a 1 up top, I get a 4 in the bottom. So this limit is equal to 1/4. Next, letter E. The limit as x approaches infinity of 2x squared minus 5 over x plus 3. Remember, the limit as x goes to infinity is really the same thing as a horizontal asymptote. So we compare the degrees of the numerator and the denominator to this. So the numerator has a degree of 2, the denominator has a degree of 1. So since the degree of the top is larger, this limit does not exist. All right, F, another limit as x approaches infinity, this time of 2, actually E was 2x minus 5 over x plus 3. F is actually 2x squared minus 5 over x plus 3, so I'll just switch them around. All right, this will be 2x minus 5 all over x plus 3. So just so there's no confusion, this is going to be E, and this was F. All right, well here again, as x approaches infinity, we want to compare the degrees. All right, so the degree of the numerator is 1, the degree of the denominator is 1. Since they're equal, all we do is take the ratio of the leading coefficients. So 2 over 1, just 2. All right, G, we have another limit as x goes to infinity of 2x minus 5 over x squared plus 3. All right, so again, the limit as x goes to infinity, we compare the degree of the numerator to the degree of the denominator. Degree of the numerator is 1, degree of the denominator is 2. Since the degree of the bottom is larger, the limit is 0. And finally, h. Here we have the limit as x approaches 2 from the left-hand side of 2x minus 5 over x minus 2. All right, so we can try direct substitution here. We're going to get negative 1 over 0. When it's an overall limit and we get a number over 0, we say it does not exist. But when it's a one-sided limit coming from the left or coming from the right, in this case coming from the left, we can always answer. Now we know that as a graph approaches a vertical asymptote, which when the top is not bottom and when the top is not 0 but the bottom is 0, we will always have a vertical asymptote. And as a graph approaches a vertical asymptote, it only has two options. It can either go to positive infinity or negative infinity. All right, so what we're going to do here is take a number really, really close to 2, but because of this little minus sign after it, to the left of 2. So on a number line, right to the left of 2, 1.9. All right, we're going to plug it in here. We don't care what the actual numbers are, we just care about the signs. If I plug 1.9 in for x in the numerator, I'm going to get 3.8 minus 5, which is a negative number. If I plug 1.9 in here, 1.9 minus 2 is also a negative number. Well, a negative over a negative is positive, so this will go to positive infinity. All right, number 12. It says draw the graph of a function that has a removable discontinuity, b, a jump discontinuity, and c, an infinite discontinuity. All right, the important things to really know here, all right, a removable discontinuity all right, is a hole. All right, so something like this. That's a removable discontinuity, where you literally just took a point out of the graph and moved it to somewhere. That's why it's called removable. All right, a jump discontinuity is where if you're trying to trace this with a pencil, you literally have to jump. The best example of these are piecewise functions. Right? So if you have something like this, and then maybe you have something like this. All right, so if you're trying to trace this, you have to take your pencil and jump up to the next piece. All right, and C, an infinite discontinuity, is a vertical asymptote, right? So if you have something like this, rational functions often have infinite discontinuities. And it doesn't matter whether they both go up, one goes up, one comes down, it doesn't really matter as long as there's a vertical asymptote there. All right, 13. Sketch the graph of each function. Be sure to include the intercepts and asymptotes in your sketch. Right, so those are rational functions. Again, we're not going to be doing any graphing here, but do remember kind of your key features of rational functions, right? Your x-intercepts, your y-intercepts, your asymptotes, that kind of stuff. Of course, you're never going to have to graph them, but you may be asked, what is the x-intercept? What is the vertical asymptote? Something like that. So just remember that to find an x-intercept, you set the top equal to 0 and solve. To find a y-intercept, you plug 0 in for x. To find a horizontal asymptote, that's your limit as x goes to infinity, where you compare the degrees of the numerator and denominator. To find a vertical asymptote, you set the denominator equal to 0 and solve. And then we had our slant asymptotes and that kind of stuff, but we won't get too deep into that in the final exam. All right, number 14, find the quotient and remainder when x to the fourth minus 2x cubed plus 15x minus 2 is divided by x plus 2. Right, well, we can either use long division or synthetic division here. Synthetic division is much easier, and we can use synthetic division because the divisor is of the form x minus c. Right, so in my box, I put the 0 of this, which would be negative 2. My coefficients going across are 1, negative 2. I am missing a squared term. We do have to put the 0 in for that. Right, that's very important. Then we bring this down, we multiply, we add, we multiply, we add, we multiply, we add, we multiply, we add. Okay, so that worked out very nicely. There is no remainder, right? So our divisor would be x cubed minus 4x squared plus 8x minus 1. And there is no remainder, so we don't have to worry about that. All right. Next problem. 15. Find all real zeros of f of x is equal to x cubed minus x squared plus 15x minus 2. Oh no, I totally started going to the problem above, so totally messed that up. X cubed minus x squared. Whoa, we need a bigger one than that. X cubed minus x squared minus 10x plus 8. Okay, so there's a few ways to do this. All right. I'll assume that this is on the non-calculator portion. Obviously, calculator portion makes this very easy. All right, but we can do our P over Q's. All right, and remember that's all the factors of your constant divided by all the factors of your leading coefficient, which is just 1. So this is plus or minus 8, plus or minus 4, plus or minus 2, plus or minus 1. Okay, so we want to kind of check these and see which ones are zeros. I'll check the easy ones kind of mentally first, all right, before you can always do synthetic division and use the remainder theorem, factor theorem. All right, so I'll try 1 first. So you get 1 minus 1, which is 0, minus 10 plus 8, negative 2. Nope, that doesn't work. Let's try negative 1. This becomes negative 1. All right, minus 1 is negative 2. Plus 10 is 8, plus 8 is 16. Nope. Let's try 2. 8 minus 4 is 4. Minus 20 is negative 16 plus 8. Nope. Negative 2, we get negative 8. Minus 4, which is negative 12. Plus 20, which is 8, plus 8 is 16. Nope. All right, so let's try 4. So we have 1, 4, 3, 12, 2, 8, 16. Nope, that does not work. Let's try negative 4. 1, negative 1, negative 10, 8. So we get 1, negative 4, negative 5, 20, 10, negative 40. Nope. That does not work. All right, let's try 8. So we get 1, 8, negative 7, negative 56. No way this works. A huge negative number. So a massive negative number here. Nope. So none of these work thus far. All right, let's try negative 8. Oh, and when I did 8, I totally did not cube that, so I did not do that. I don't think I did 4 correctly either. Okay, so let's see, we did that. Okay, so 4 cubed would be 64, minus 16 is 48, minus 40 is negative 8. Ooh, that might actually work. So let's look at 4. How did I mess this up if it works? So 1, 4, 3, 12, 2, 8. Yeah, no, that doesn't work. Son of a biscuit. Alright, so maybe I didn't mess up. Negative 4, 1, negative 1, negative 10, 8, 1, negative 4, negative 5, 20, 10, negative 40, nope. Okay, so I didn't mess up. Let's try 8, or negative 8 rather. 1, negative 1, negative 10, 1, no way. Okay, so none of these work. Okay, then this would have to be on the calculator portion. Again, unless we made a mistake somewhere. So let's go ahead and take a look at this. Alright, so we say x cubed minus x squared minus 10x plus 8. Okay. So, yep. And this definitely can't actually be 3. Oops. Alright, let's go to negative 5, 0. Okay, yeah, so they're all irrational, it appears. Alright, so we can say, alright, well, x is equal to negative 3.084. And then we do this again. And we say 0, 2, enter, 0.787. And we do this again. And 3.297. Alright, so they're all irrational, so we would definitely have to use our calculator for that one. Alright, 16. Given f of x is equal to 2x plus 3 over 5x minus 2, find the inverse of f of x, state the domain and range of f of x. Alright, we won't really worry about the domain and range. All I'll ask you to do is find the inverse. Alright, so we think of this as y, and then we switch our x's and our y's. Alright, then we have to solve for y again. So first I'm going to multiply both sides by 5y minus 2. Alright, then I go ahead and distribute here, so I'll get 5xy minus 2x is equal to 2y plus 3. Then we want to get all of our y's on the same side, so I subtract 2y from both sides, and I add 2x to both sides. That way these cancel and these cancel. We end up with 5xy minus 2y is equal to 2x plus 3. Then here we factor out the y, and we're left with 5x minus 2 equals 2x plus 3. And I simply divide both sides by 5x minus 2. So, although a lot of you may be thinking that this was done incorrectly, because it is the exact same thing that we started with. Alright, that just means that this thing is its own inverse, and that it is symmetric about the line y equals x. So it changes this to f inverse of x. And we are done with that one. Alright, let's go to 17. So 18 says to write log base 5 of u equals 13 in exponential form. Now remember, our definition of logarithm says that log base b of a is equal to x if and only if b to the x equals a. Alright, so all I have to do to write this in exponential form is take it from here and put it in here. So 5 to the 13 equals u. Done. 18 says, find the domain of log base 5 of 2x plus 1. Okay, now we know that our parent function, log base 5, would just look like this, all right, which would be from 0 to infinity, not including 0. All right, well, what does this do here, right? Well, we have two different transformations going on. All right, first, we have a horizontal shrink by 2, which is taking it by a half, right? And then it's moving it to the left 1. Well, this horizontal shrink is actually going to change how far it's going to go to the left. So instead of going to the left 1, we actually only go to the left 1/2. So the domain here is going to be from negative 1/2 to infinity. All right, 19. Evaluate log base 2 of 52. All right, well, this would have to be on a calculator portion because 52 is not a power, a nice neat power of 2. So you could either just plug this right into your calculator. All right, we can say math up times to log base. Oh, come on. We can say log base 2 of 52 equals 5.700. Good times. All right, number 20 says to solve 8 to the 6 plus 3x equals to 4. All right, well, I can change this 8 to 2 cubed, and then I still have to the 6 plus 3x power. And I can change 4 to 2 squared. When I have a power raised to a power, I multiply them. Do remember to distribute here. So this is really 2 to the 18 plus 9x is equal to 2 squared. Well, now that my bases are the same, I can just set my exponents equal to each other. So 18 plus 9x equals 2. Subtract 18 from both sides. We get 9x is equal to negative 16. Divide. So x is equal to negative 16/9. And we are done. 21. Solve log base x of 64 equals negative 3. Okay, so if we use our definition of logarithm, this translates to x to the negative third power is equal to 64. All right, so what to the negative third power would be 64. You can really actually just raise both sides to the negative 1/3 power, All right, so this will just give you x to the first, which is just x. And 64 to the negative 1/3 power is simply 1 over the cubed root of 64. Cubed root of 64 is 4, so this is just 1/4. 22. Solve log base 10 of 7x minus 12 is equal to 2 log base 10 of x. Alright, well, we want to use the if log base b of x equals log base b of y, then x must equal y. But before we can do that, we have to move this 2 up here as an exponent. And then we can say 7x minus 12 is equal to x squared. Well, then we can set this equal to 0, and we get x squared minus 7x plus 12 is equal to 0. So this factors to x minus 3 and x minus 4. All right, therefore x is equal to 3 and 4. Done. All right, 23. ln of e to the x equals what? All right. Well, really, the ln and the e undo each other. It just equals x. All right. Similarly, 24. E to the ln of x equals what? Same thing. The e and the ln cancel out. All right. Of course, you can use the definition of logarithm to kind of do it the slightly longer way, but it works just fine that way as well. I'm going to go ahead and stop here for today, and we'll pick this up tomorrow. I'll be putting out a couple of more videos tomorrow that will finish up the review.